Quantitative metrics form the backbone of contractor performance analysis, providing a structured and objective approach to evaluating the efficiency, reliability, and overall effectiveness of contractors engaged in complex projects. Central to this framework is the development and application of key performance indicators, KPIs, which serve as measurable benchmarks against which contractor performance can be systematically assessed. Among the most widely utilized KPIs in this domain are the Cost Performance Index, CPI, the Schedule Performance Index, SPI, and profit margin calculations. Each of these metrics is deeply rooted in both theoretical constructs and practical methodologies, offering unique insights into various dimensions of contractor behavior and project outcomes. The Cost Performance Index is a fundamental metric derived from Earned Value Management, EVM, a project management methodology that integrates scope, schedule, and cost data. CPI quantifies the cost efficiency of a contractor by comparing the value of work performed to the actual costs incurred. A CPI greater than 1 indicates cost efficiency, while a value less than 1 reveals cost overruns. To compute this metric effectively, it is crucial to accurately measure the earned value, EV, of completed work, a process that requires rigorous data collection, precise documentation, and consistent updates throughout the project lifecycle. Historical studies in project management underscore the importance of CPI as an early warning system, allowing stakeholders to identify inefficiencies before they escalate. However, reliance on CPI alone can be misleading in scenarios where cost overruns are intentionally deferred or masked through manipulative accounting practices. This limitation necessitates cross-referencing CPI data with other financial and operational metrics to ensure a holistic analysis. Similarly, the Schedule Performance Index offers critical insights into a contractor's ability to meet project deadlines by comparing the value of work performed to the planned value, PV, of scheduled work. SPI values exceeding 1 indicate that a project is ahead of schedule, while values below 1 signify delays. Unlike CPI, SPI focuses on time rather than cost, making it an indispensable tool for assessing time-sensitive projects. The theoretical underpinnings of SPI trace back to Gantt chart methodologies and critical path analysis, which prioritize the sequencing and timing of project activities. Practically, SPI is most effective when paired with detailed project schedules that account for potential contingencies and external variables. However, its accuracy depends heavily on the granularity of baseline schedules and the consistency of progress reporting. For example, discrepancies between planned and actual timelines may arise due to unforeseen site conditions, resource constraints, or regulatory hurdles. This highlights the importance of integrating SPI with risk management frameworks that address such uncertainties comprehensively. Profit margins, another cornerstone metric, provide a direct measure of financial performance by evaluating the difference between project revenues and costs. In contractor performance analysis, profit margins are often examined in the context of specific project types, market conditions, and contractor size. The historical evolution of profit margin analysis reveals its roots in economic theories of value and utility, which emphasize the balance between cost minimization and value maximization. Contemporary practices build upon these foundations by incorporating advanced financial modeling techniques, such as scenario analysis and sensitivity analysis, to predict profit variability under different conditions. While profit margins offer a straightforward indication of financial success, their interpretation requires careful consideration of context-specific factors, such as contractual agreements, project scope, and external economic trends. For instance, a high profit margin on a small-scale project may not equate to long-term sustainability if the contractor fails to secure repeat business or maintain competitive pricing. The application of these metrics extends beyond simple measurement, serving as tools for dynamic decision-making and strategic planning. Contractors often utilize CPI, SPI, and profit margins to refine their bidding strategies, allocate resources more efficiently, and identify areas for process improvement. From the perspective of surety bond underwriters, these metrics are invaluable for assessing contractor reliability and determining bond capacity. By analyzing historical trends in CPI and SPI, underwriters can predict future performance and evaluate the likelihood of project completion within budget and on schedule. Furthermore, profit margins provide critical insights into a contractor's financial stability, informing risk assessments and underwriting decisions. Recent advancements in data analytics have further enhanced the applicability of these metrics, enabling the integration of machine learning algorithms to identify hidden patterns and correlations within historical project data. Interdisciplinary connections also enrich the analysis of contractor performance metrics, linking them to broader fields such as economics, operations research, and behavioral science. For example, behavioral economics provides insights into the decision-making biases that may influence contractor performance, such as optimism bias or loss aversion. Understanding these psychological factors allows for the development of more nuanced risk assessment models that account for both quantitative and qualitative dimensions. Similarly, operations research contributes optimization techniques for resource allocation and schedule management, ensuring that performance metrics are grounded in practical solutions rather than theoretical ideals. The integration of these disciplines underscores the complexity of contractor performance analysis and the need for a multidimensional approach that transcends traditional silos. Contemporary debates surrounding the use of quantitative metrics in contractor performance analysis often center on the tension between standardization and customization. Standardized metrics such as CPI and SPI offer the advantage of comparability across projects and contractors, facilitating industry-wide benchmarking and performance tracking. However, critics argue that these metrics may oversimplify complex realities, failing to capture unique project characteristics or contractor-specific challenges. Customization, on the other hand, allows for tailored metrics that reflect the distinct needs and priorities of individual stakeholders. For instance, a contractor specializing in renewable energy projects may prioritize metrics related to environmental impact and sustainability, while a contractor in the healthcare sector may emphasize patient safety and regulatory compliance. Balancing these competing demands requires a flexible framework that accommodates both standardization and customization without compromising analytical rigor. The historical context of performance metrics further illuminates their evolution and ongoing relevance. Early efforts to quantify contractor performance were often limited to basic financial ratios and anecdotal evidence, reflecting the lack of systematic methodologies and reliable data sources. The advent of project management tools in the mid-20th century marked a turning point, introducing more sophisticated metrics and analytical techniques. Over time, these tools have evolved to incorporate real-time data tracking, predictive analytics, and automated reporting, transforming the landscape of contractor performance analysis. Today, the increasing availability of big data and cloud-based platforms offers unprecedented opportunities for scalability and collaboration, enabling stakeholders to access and analyze performance metrics with greater accuracy and efficiency. The role of technology in advancing contractor performance analysis cannot be overstated. Modern project management software provides comprehensive dashboards that integrate CPI, SPI, and profit margin data, allowing stakeholders to visualize trends and identify anomalies in real time. Artificial intelligence and machine learning further enhance these capabilities by automating data analysis and generating actionable insights. For example, predictive models can identify early warning signs of cost overruns or schedule delays, enabling proactive interventions that mitigate risks and improve outcomes. Additionally, blockchain technology offers potential applications in verifying data integrity and ensuring transparency in contractor reporting, addressing long-standing concerns about accuracy and accountability in performance metrics. The process of data collection and verification in contractor risk assessment is a cornerstone of reliable decision-making in surety bond underwriting. Ensuring that historical project data is both accurate and comprehensive is critical for evaluating a contractor's capacity to meet future obligations, manage risk effectively, and adhere to contractual requirements. This process is not merely an administrative exercise, but a rigorous and multifaceted undertaking that blends technical acumen, analytical methodologies, and interdisciplinary insights to generate a clear and actionable risk profile. Data collection begins with identifying the key sources of information, which can include the contractor's internal records, third-party audits, government filings, industry benchmarks, and client testimonials. Each of these sources offers unique insights, but they also pose distinct challenges in terms of accessibility, reliability, and consistency, necessitating a systematic approach to data acquisition and validation. Theoretical frameworks for data collection emphasize the importance of structured methodologies to ensure consistency and comparability across projects and contractors. One widely applied model is the Total Quality Management (TQM) approach, which prioritizes continuous improvement in data accuracy through robust documentation practices and regular feedback loops. In this context, the collection process often begins with an in-depth review of contractor-submitted documentation, including financial statements, project schedules, bid proposals, and cost breakdowns. These documents provide the raw data needed to analyze key performance indicators, such as profit margins, cost efficiency, and schedule adherence. However, reliance on contractor-provided data alone is fraught with risks, as it may be incomplete, outdated, or intentionally misrepresented. To mitigate these risks, data collection must incorporate third-party verification mechanisms, such as credit reports, lien searches, and supplier references, which serve as independent checks on the contractor's self-reported information. The role of technology in data collection has evolved significantly over the past few decades, transforming what was once a labor-intensive process into a streamlined and automated workflow. Modern tools such as enterprise resource planning, ERP systems, and cloud-based project management platforms enable real-time data tracking, ensuring that information is up-to-date and accessible to all stakeholders. Additionally, the integration of artificial intelligence and machine learning algorithms has opened new avenues for predictive analytics, allowing underwriters to identify patterns and anomalies that may not be immediately evident through manual analysis. For instance, algorithms can cross-reference contractor data with industry benchmarks to flag discrepancies in cost estimates or project timelines, thereby providing early warnings of potential risks. Blockchain technology further enhances data reliability by creating immutable records that prevent tampering and ensure transparency throughout the data lifecycle. These technological advancements underscore the increasing importance of digital literacy and technical expertise in the field of contractor risk assessment. Verification of data authenticity is a critical step that ensures the integrity of the risk assessment process. This involves cross-checking the collected data against multiple independent sources to confirm its accuracy and completeness. Techniques such as forensic accounting are particularly valuable for uncovering discrepancies in financial records, such as inflated revenues or hidden liabilities. Similarly, site visits and physical inspections provide first-hand insights into the contractor's operational capabilities, allowing underwriters to assess whether the reported data aligns with on-the-ground realities. For example, a contractor claiming extensive experience with large-scale infrastructure projects may be exposed as overstating their capabilities if their facilities lack the necessary equipment or personnel to support such undertakings. These verification activities must be meticulously documented to ensure a clear audit trail, which is essential for regulatory compliance and future reference. Identifying gaps in historical project data is another essential aspect of the verification process. Data gaps can arise from various sources, including poor record keeping, changes in management, or the dissolution of subcontractor relationships. These gaps pose significant challenges, as they obscure the contractor's true performance history and introduce uncertainties into the risk assessment. Advanced gap analysis techniques, such as Monte Carlo simulations and Bayesian inference models, can be employed to estimate the potential impact of missing data and guide the decision-making process. Additionally, qualitative methods, such as interviews with former clients or employees, can provide context and fill in critical details that may not be captured in quantitative records. By combining quantitative and qualitative approaches, underwriters can develop a more nuanced understanding of the contractor's historical performance, even in the presence of incomplete data. The risks associated with incomplete or falsified records cannot be overstated, as they have far-reaching implications for both project outcomes and underwriting decisions. Falsified records, in particular, represent a deliberate attempt to mislead stakeholders and can result in significant financial and reputational losses. Detecting such fraud requires a combination of advanced analytical tools and human expertise. Data triangulation, which involves cross-referencing information from multiple independent sources, is an effective method for identifying inconsistencies and red flags. For instance, discrepancies between reported project costs and supplier invoices may indicate fraudulent activity, while unusually high profit margins on specific projects could signal underreported expenses or overbilling. Beyond financial records, non-financial indicators, such as high employee turnover or frequent legal disputes, can also serve as warning signs of deeper issues within the contractor's operations. Interdisciplinary connections further enrich the process of data collection and verification, drawing on fields such as statistics, behavioral science, and regulatory compliance to enhance analytical rigor. Statistical methods, such as regression analysis and time series modeling, enable underwriters to identify trends and correlations within historical data, providing a more comprehensive picture of contractor performance. Behavioral science, on the other hand, sheds light on the psychological factors that may influence contractor behavior, such as risk aversion or overconfidence, which can affect the reliability of self-reported data. Regulatory frameworks, including those established by organizations such as the Financial Accounting Standards Board, FASB, and the International Organization for Standardization, ISO, provide guidelines for data accuracy and transparency, ensuring that contractors adhere to industry best practices. Contemporary debates in the field often center on the trade-offs between data accessibility and confidentiality. While greater transparency enhances the reliability of risk assessments, it also raises concerns about the privacy and security of sensitive information. These concerns are particularly pronounced in the context of public-private partnerships, where contractors may be required to disclose proprietary data to government agencies or financial institutions. Balancing these competing interests requires the development of robust data governance policies that protect confidentiality without compromising analytical integrity. Additionally, the increasing use of third-party data providers introduces questions about data ownership and accountability, highlighting the need for clear contractual agreements and ethical guidelines in data sharing arrangements. The historical evolution of data collection and verification practices reveals a gradual shift from manual processes to automated systems, reflecting broader trends in technology adoption and data-driven decision-making. Early practices relied heavily on paper records and manual audits, which were time-consuming and prone to human error. The introduction of computerized databases in the late 20th century marked a significant milestone, enabling faster and more accurate data retrieval. In recent years, the rise of big data analytics and cloud computing has further transformed the landscape, allowing for the integration of large and complex data sets from diverse sources. This evolution underscores the dynamic nature of the field and the ongoing need for professionals to adapt to emerging technologies and methodologies. The integration of environmental, social, and governance (ESG) factors into contractor risk assessment represents a growing area of focus, reflecting broader societal demands for sustainability and ethical business practices. ESG data collection involves evaluating contractors' environmental impact, labor practices, and corporate governance structures to identify risks that may not be captured by traditional performance metrics. For example, a contractor with a history of environmental violations may face regulatory fines or reputational damage that could affect their ability to complete future projects. By incorporating ESG criteria into the data collection and verification process, underwriters can develop a more comprehensive risk profile that aligns with the evolving expectations of stakeholders and regulators. Project scope complexity is a critical determinant of contractor risk, shaping the parameters within which contractors must operate and directly influencing the likelihood of project success or failure. The scope of a project defines its objectives, deliverables, timelines, and resource requirements, and its complexity arises from the interplay of factors such as scale, stakeholder involvement, regulatory requirements, technological integration, and environmental conditions. Evaluating contractor performance within this framework requires a deep understanding of how contractors have navigated the challenges associated with past projects of varying scope and complexity. This evaluation serves as a predictor of future performance, providing insights into a contractor's capacity to manage intricate operations, adapt to unforeseen changes, and deliver results within the agreed parameters. The theoretical foundation for analyzing project scope complexity lies in systems theory, which views projects as interconnected networks of tasks, resources, and stakeholders. Complexity arises when these components interact in non-linear and often unpredictable ways, leading to emergent behaviors that are difficult to anticipate or control. In practical terms, this means that larger projects with multiple interdependencies, such as infrastructure development or industrial construction, present significantly greater risks than smaller, more straightforward endeavors. Contractors operating in these environments must demonstrate advanced capabilities in project management, resource allocation, and risk mitigation. Key performance indicators such as schedule adherence, cost efficiency, and quality control provide measurable benchmarks for assessing their ability to handle complexity. But these metrics must be interpreted in the context of the specific challenges posed by each project's scope. Scope changes, often referred to as scope creep, introduce additional layers of complexity that can profoundly impact project outcomes. Scope creep occurs when the original project scope expands beyond its initial parameters, typically due to evolving client demands, unforeseen technical challenges, or regulatory changes. While minor scope adjustments are common and often necessary, unmanaged scope creep can lead to cost overruns, schedule delays, and quality issues, significantly increasing contractor risk. Evaluating a contractor's historical performance in managing scope changes involves examining their ability to negotiate contract amendments, allocate additional resources efficiently, and maintain stakeholder communication. Research in project management highlights that contractors who adopt proactive change management strategies, such as clearly defining scope boundaries, conducting regular scope reviews, and utilizing formal change request processes, are better equipped to mitigate the risks associated with scope creep. Innovation and emerging technologies further complicate the evaluation of contractor performance in complex projects, as they introduce new variables that can both enhance and disrupt traditional workflows. Contractors who leverage innovative practices, such as building information modeling, BIM, modular construction techniques, or advanced materials, often gain a competitive edge by improving efficiency, reducing waste, and accelerating timelines. However, the adoption of these technologies also carries inherent risks, including steep learning curves, high initial costs, and potential integration challenges with existing systems. Assessing contractor performance in this context requires a nuanced understanding of their ability to balance the benefits of innovation against its associated risks. For instance, a contractor's track record in deploying BIM on past projects can reveal insights into their technical expertise, adaptability, and capacity to collaborate with other stakeholders in a technology-driven environment. The impact of project scope complexity on contractor risk is also shaped by external factors, such as regulatory requirements, environmental conditions, and stakeholder dynamics. Large-scale projects in sectors such as energy, transportation, or healthcare often face stringent regulatory oversight, requiring contractors to navigate complex permitting processes, comply with safety and environmental standards, and address community concerns. These external pressures can exacerbate the challenges of managing scope complexity, particularly for contractors with limited experience in highly regulated environments. Historical performance data, such as the frequency and severity of regulatory violations, provide valuable indicators of a contractor's ability to operate within these constraints. Similarly, environmental factors such as geographic location, climate conditions, and site accessibility introduce unique challenges that must be accounted for in the risk assessment process. Contractors with a history of successfully managing projects in remote or hazardous locations demonstrate a level of resilience and adaptability that is critical for mitigating the risks associated with environmental complexity. Interdisciplinary approaches to understanding project scope complexity draw on fields such as behavioral science, organizational theory, and data analytics to provide deeper insights into contractor performance. Behavioral science, for example, sheds light on the decision-making processes of contractors and their teams, highlighting cognitive biases such as overconfidence or anchoring that can influence their approach to complex projects. Organizational theory examines the internal structures and processes that enable contractors to manage complexity, such as hierarchical versus decentralized decision-making models or the use of cross-functional teams. Data analytics, meanwhile, offers powerful tools for analyzing historical project data to identify patterns, trends, and correlations that may not be immediately apparent through manual review. For instance, Machine learning algorithms can be used to predict the likelihood of scope-related delays or cost overruns based on past project characteristics, providing underwriters with actionable insights into contractor risk. Contemporary debates in the field often center on the trade-offs between flexibility and control in managing project scope complexity. On one hand, contractors who adopt flexible approaches, such as agile project management or integrated design-build models, are better positioned to adapt to changing circumstances and stakeholder demands. On the other hand, excessive flexibility can lead to a lack of accountability, unclear responsibilities, and inconsistent outcomes, undermining the stability and predictability that stakeholders value. Balancing these competing priorities requires contractors to establish clear governance frameworks that define roles, responsibilities, and decision-making authority, while allowing for controlled adjustments to scope as needed. This balance is particularly important in collaborative delivery models, where multiple contractors and stakeholders must work together to achieve shared objectives. Historical trends in managing project scope complexity reveal the evolving nature of contractor risk and the strategies used to address it. In the mid-20th century, project management practices were largely linear and hierarchical, emphasizing rigid scope definitions and top-down decision-making. While this approach provided clarity and control, it often struggled to accommodate the dynamic and multifaceted nature of complex projects. The rise of systems thinking in the latter half of the century marked a shift toward more holistic and adaptive methodologies, enabling contractors to better navigate the uncertainties and interdependencies of large-scale projects. Today, the integration of digital tools and data-driven techniques has further transformed the landscape, offering unprecedented levels of precision, efficiency, and collaboration in managing project scope complexity. The role of stakeholder engagement in addressing project scope complexity cannot be overstated, as stakeholders play a central role in defining scope, approving changes, and evaluating outcomes. Effective stakeholder engagement involves building trust, fostering open communication, and aligning expectations across diverse groups, including clients, investors, regulators, and community members. Contractors with a history of successful stakeholder management demonstrate a capacity to navigate the often competing interests and priorities of these groups, reducing the risk of conflicts, delays, and reputational damage. For example, a contractor's ability to secure community buy-in for a controversial infrastructure project may hinge on their willingness to address local concerns, provide transparent information, and adapt project plans to mitigate negative impacts. Emerging research on project scope complexity highlights the growing importance of resilience and adaptability in contractor performance. Resilience refers to the ability to recover from setbacks and disruptions, while adaptability involves the capacity to adjust strategies and processes in response to changing conditions. These qualities are particularly critical in an era characterized by rapid technological advancements, shifting regulatory landscapes, and increasing global uncertainty. Contractors who demonstrate resilience and adaptability in their approach to complex projects are better equipped to manage risk, maintain stakeholder confidence, and deliver successful outcomes despite the inherent challenges of scope complexity. Failure analysis in historical project data is a critical aspect of contractor risk assessment, providing a structured framework for identifying recurring patterns of underperformance and uncovering the root causes of project failures. By examining instances of delays, cost overruns, and litigation in past projects, stakeholders can gain insights into systemic vulnerabilities and specific contractor behaviors that increase risk. This analytical process combines quantitative methods with qualitative reasoning to distinguish between failures arising from external factors, such as regulatory changes or market fluctuations, and those directly attributable to the contractor's performance, such as mismanagement or technical incompetence. The ability to dissect these failures comprehensively is essential for ensuring that underwriting decisions and risk mitigation strategies are informed by an accurate and holistic understanding of historical trends. Theoretical frameworks for failure analysis are rooted in disciplines such as engineering, systems theory, and organizational behavior, each of which provides unique perspectives on identifying and interpreting patterns of failure. Engineering approaches often emphasize fault tree analysis, FTA, and failure mode and effects analysis, FMEA, which decompose complex systems into their constituent parts to trace the pathways through which failures occur. Systems theory broadens this perspective by examining the interdependencies and feedback loops within a project, highlighting how small disruptions in one area can cascade into broader failures. Organizational behavior focuses on human and structural factors, such as leadership decisions, communication breakdowns, and organizational culture, which can contribute to the recurrence of project failures. Together, these frameworks provide a multidisciplinary foundation for evaluating failure patterns and developing strategies to prevent their recurrence. Historical project data serves as the primary input for failure analysis, encompassing a wide range of quantitative and qualitative information. Quantitative data includes metrics such as baseline and actual project timelines, budgeted versus actual costs, and the frequency and severity of legal disputes. These metrics allow analysts to identify deviations from expected performance and quantify their financial and operational impacts. Qualitative data, such as contractor correspondence, stakeholder interviews, and litigation case summaries, provide contextual details that illuminate the circumstances surrounding failures. For example, an analysis of project delays may reveal that late material deliveries were due to supply chain disruptions, while cost overruns could be linked to inaccurate initial estimates or scope changes. By integrating these data sources, analysts can construct a comprehensive narrative of each failure event, identifying both the proximate triggers and the underlying causes. The process of identifying patterns in failure data involves statistical analysis, data visualization, and machine learning techniques to uncover correlations and trends. Statistical methods, such as regression analysis and hypothesis testing, are used to quantify the relationships between variables and determine the likelihood of recurrence under similar conditions. Data visualization tools, such as heat maps and trend lines, enable analysts to identify clusters of failures within specific project types, geographic regions, or time periods. Machine learning algorithms, including clustering and anomaly detection, offer more advanced capabilities for identifying subtle patterns and outliers that may not be immediately apparent through traditional analysis. For instance, clustering algorithms can group projects with similar failure characteristics, such as frequent delays in urban infrastructure projects, while anomaly detection can highlight instances where a contractor's performance deviates significantly from industry norms. Root cause analysis, RCA, is a central component of failure analysis, aiming to identify the fundamental reasons why failures occur rather than merely addressing their symptoms. RCA methodologies typically follow a structured process that includes problem identification, causal factor analysis, and solution development. Techniques such as the 5 whys method, fishbone diagrams, and causal loop diagrams are commonly used to trace the chain of events leading to a failure and pinpoint its root causes. For example, a project delay initially attributed to subcontractor non-performance may, upon closer examination, reveal deeper issues such as inadequate vetting processes or unrealistic scheduling expectations imposed by the contractor. Similarly, litigation over construction defects may expose deficiencies in quality control procedures or gaps in compliance with industry standards. RCA not only enhances the accuracy of failure analysis, but also provides actionable insights for improving contractor practices and mitigating future risks. The distinction between failures stemming from external factors and those attributable to contractor performance is a critical element of failure analysis, as it influences how risks are allocated and managed. External factors such as economic downturns, natural disasters, and changes in government policy are often beyond the contractor's control but can have significant impacts on project outcomes. For instance, a sudden increase in material costs due to global supply chain disruptions may lead to budget overruns, while new environmental regulations may necessitate costly design changes. Identifying these factors requires a thorough understanding of the broader context in which the project operates, as well as the contractor's ability to adapt to changing conditions. Conversely, failures linked to contractor performance are typically the result of poor planning, inadequate resource management, or lack of technical expertise. For example, a contractor's inability to meet deadlines may stem from insufficient staffing or ineffective project scheduling, while cost overruns may be caused by a failure to accurately estimate material quantities or account for contingency expenses. Differentiating between these causes is essential for assigning responsibility and developing targeted risk mitigation strategies. Interdisciplinary connections enrich the practice of failure analysis by integrating insights from fields such as behavioral science, economics, and legal studies. Behavioral science explores the cognitive biases and decision-making processes that contribute to failures, such as overconfidence in project timelines or resistance to acknowledging risks. Economics provides tools for assessing the cost implications of failures and evaluating the trade-offs between risk and reward in contractor performance. Legal studies offer a framework for analyzing litigation data and understanding the contractual obligations and liabilities that shape project outcomes. For example, a behavioral analysis of contractor decision-making may reveal a tendency to underestimate the likelihood of adverse events, while an economic analysis may highlight the financial impact of these misjudgments. Similarly, a legal review of past disputes may uncover recurring patterns of contract breaches or liability issues that indicate areas of concern. Contemporary debates in failure analysis often revolve around the balance between transparency and accountability in data sharing. While greater transparency enhances the reliability of failure analysis by providing access to comprehensive and accurate data, it also raises concerns about confidentiality and reputational damage for contractors. These concerns are particularly pronounced in cases involving sensitive litigation or regulatory violations, where public disclosure could have significant legal and financial repercussions. Addressing these challenges requires the development of ethical guidelines and data governance policies that protect contractor confidentiality while ensuring that critical insights are not obscured. Additionally, the increasing use of predictive analytics and artificial intelligence in failure analysis has sparked discussions about the potential for algorithmic bias and the need for human oversight in interpreting analytical results. The evolution of failure analysis practices reflects broader trends in project management and risk assessment, highlighting the increasing importance of data-driven decision-making and continuous improvement. Early approaches to failure analysis were often reactive, focusing on post-mortem reviews of individual projects without systematically examining broader patterns or root causes. Over time, the adoption of more rigorous methodologies such as RCA and statistical analysis has enabled stakeholders to move toward proactive risk management by identifying early warning signs and implementing preventive measures. The integration of digital tools and big data analytics has further transformed the field, allowing for real-time monitoring and analysis of project performance. These advancements underscore the dynamic and evolving nature of failure analysis, as well as its critical role in enhancing contractor performance and mitigating risk in complex projects. Creditworthiness and financial trends in historical projects are critical factors in assessing contractor risk, providing a detailed lens through which to evaluate a contractor's financial health, stability, and capacity to meet project obligations. The examination of financial health requires a multi-dimensional analysis of historical project funding sources, payment schedules, and cash flow management practices. These components are not isolated. Instead, they interact dynamically to shape the contractor's financial resilience and ability to withstand project-specific challenges or broader economic disruptions. A robust understanding of these financial dimensions is essential for underwriters, project owners, and other stakeholders who rely on accurate risk assessments to make informed decisions. Historical project funding serves as the foundation for evaluating a contractor's financial health, revealing patterns in their access to capital and ability to secure competitive financing. This aspect of analysis involves scrutinizing the sources of project funding, which may include internal reserves, bank loans, bonds, or equity investments. Each funding source carries distinct implications for risk assessment. For instance, reliance on short-term loans may indicate potential liquidity challenges, while a heavy dependence on external equity partners could suggest vulnerability to stakeholder disputes or changing market conditions. Theoretical frameworks such as the Modigliani-Miller theorem, which explores the cost of capital in varying financial structures, provide a foundation for understanding how funding decisions impact contractor risk. Practical applications of this analysis include evaluating the terms and conditions of funding agreements, such as interest rates, repayment schedules, and covenants, to identify potential financial constraints or vulnerabilities. Payment delays represent another critical area of financial analysis, offering insights into the contractor's operational efficiency and relationships with clients and suppliers. Chronic payment delays may signal deeper issues, such as poor cash flow management, misaligned project schedules, or strained client-contractor relationships. The ripple effects of payment delays can be severe, extending beyond the contractor to impact subcontractors, suppliers, and other stakeholders. Data on the frequency and duration of payment delays in historical projects provides a valuable metric for assessing the contractor's financial discipline and reliability. Additionally, examining the causes of these delays, whether they stem from client disputes, administrative inefficiencies, or unexpected project challenges, helps differentiate between external and internal factors affecting the contractor's financial performance. Payment trends can also highlight systemic risks within certain industries or regions, emphasizing the importance of contextual analysis in financial risk assessment. Cash flow management is perhaps the most direct indicator of a contractor's financial stability, reflecting their ability to balance incoming and outgoing funds in real time. Effective cash flow management ensures that the contractor can meet payroll, procure materials, and address unforeseen expenses without compromising project progress. Historical cash flow data provides a window into the contractor's financial practices, revealing patterns of liquidity stress, overextension, or strategic reserve allocation. The analysis of cash flow trends often involves calculating key ratios, such as the current ratio or quick ratio, which measure the contractor's ability to meet short-term obligations. These ratios, when examined over multiple projects, can identify recurring liquidity issues or periods of financial strain. Additionally, cash flow data can be integrated with project milestones to evaluate whether financial performance aligns with project progress, providing a more granular view of contractor reliability. The integration of financial analysis with project outcomes creates a comprehensive framework for assessing financial risk trends over time. By correlating financial metrics with project performance indicators, analysts can identify patterns that illuminate the relationship between financial health and operational success. For example, projects with consistent funding shortfalls or payment delays may exhibit higher rates of cost overruns or schedule delays, suggesting a direct link between financial instability and project failures. Conversely, projects with stable funding and efficient cash flow management are more likely to meet or exceed performance expectations. This integration also enables the identification of leading indicators, financial metrics that precede and predict project outcomes, offering stakeholders the opportunity to intervene early and mitigate risks. Theoretical models, such as the Kaplan-Meier estimator used in survival analysis, can be adapted to analyze the duration and impact of financial stress on project outcomes, further enhancing the predictive power of this approach. Interdisciplinary connections deepen the analytical rigor of financial risk assessment by incorporating insights from economics, behavioral finance, and risk management. Economics provides a macro-level perspective, examining how market conditions, interest rate fluctuations, and fiscal policies influence contractor funding and financial performance. For instance, contractors operating in high-interest rate environments may face greater challenges in securing affordable financing, while those in inflationary markets may struggle to manage escalating material costs. Behavioral finance adds a psychological dimension, exploring how cognitive biases and decision-making heuristics affect financial practices. For example, over-optimism in revenue projections or aversion to debt may lead contractors to adopt unsustainable financial strategies. Risk management frameworks, such as enterprise risk management, (ERM), integrate these perspectives into a cohesive strategy for identifying, assessing, and mitigating financial risks across multiple projects. Contemporary debates in financial risk assessment often center on the balance between transparency and proprietary confidentiality in financial reporting. While detailed financial disclosures enhance the accuracy of creditworthiness evaluations, they also raise concerns about the exposure of sensitive information that could disadvantage contractors in competitive markets. These debates are particularly relevant in the context of privately held contractors, who may resist providing comprehensive financial data due to concerns about confidentiality or regulatory compliance. Addressing these challenges requires the development of standardized reporting frameworks that balance the needs of stakeholders with the contractor's right to privacy. For example, The adoption of financial reporting standards such as the International Financial Reporting Standards, IFRS, or Generally Accepted Accounting Principles, GAAP, provides a consistent basis for evaluating contractor financial health while ensuring comparability across projects and industries. The role of technology in financial analysis has transformed traditional practices, enabling more sophisticated and efficient methods for assessing contractor creditworthiness and financial trends. Advanced analytics platforms leverage big data and machine learning algorithms to process large volumes of financial and project data, identifying patterns and anomalies with unprecedented accuracy. For instance, predictive models can analyze historical cash flow trends to forecast future liquidity risks, while clustering algorithms can group contractors with similar financial profiles to facilitate benchmarking and peer comparisons. Blockchain technology offers additional benefits by enhancing the transparency and traceability of financial transactions, reducing the risk of fraud, and enabling real-time monitoring of payment flows. These technological advancements not only improve the reliability of financial risk assessments, but also expand the range of data sources and analytical tools available to stakeholders. The historical evolution of financial analysis in project management reflects broader trends in the professionalization and digitization of the field. Early practices relied heavily on manual record-keeping and qualitative assessments, limiting the scope and accuracy of financial evaluations. The introduction of computerized accounting systems in the mid-20th century marked a turning point, enabling more detailed and systematic analyses of financial data. In recent decades, the rise of data-driven methodologies and digital platforms has further transformed the landscape, allowing for real-time monitoring, predictive analytics, and automated reporting. These advancements underscore the dynamic and evolving nature of financial risk assessment, highlighting the need for continuous adaptation to new technologies and market conditions. Emerging trends in sustainability and corporate social responsibility, CSR, are also shaping the analysis of financial trends in historical projects. Increasingly, stakeholders are evaluating contractors' financial practices through the lens of environmental, social, and governance, ESG criteria, assessing how their funding strategies, payment practices, and cash flow management align with broader sustainability goals. For example, contractors who prioritize timely payments to suppliers and subcontractors may be viewed as more socially responsible, while those who allocate funding toward green building initiatives demonstrate a commitment to environmental stewardship. Integrating ESG considerations into financial analysis adds a new dimension to creditworthiness evaluations, reflecting the evolving priorities of investors, regulators, and the public. Risk forecasting models leveraging historical data are transformative tools in the field of contractor risk assessment, providing a quantitative framework for predicting future risks with precision and adaptability. These models integrate statistical and machine learning techniques to analyze past trends, identify patterns, and project potential outcomes, enabling stakeholders to make informed decisions about contractor reliability and project viability. The foundation of risk forecasting lies in the systematic collection and analysis of historical data, which includes metrics such as project performance indicators, financial health data, compliance records, and environmental conditions. By combining these data points with sophisticated modeling techniques, risk forecasting creates dynamic insights that evolve as new information becomes available, reducing uncertainty and improving decision-making in complex, high-stakes environments. Statistical models have long served as the backbone of risk forecasting, offering well-established methodologies for quantifying relationships and probabilities within historical data. Linear regression, logistic regression, and time series analysis are among the most widely used statistical tools for assessing contractor risk. Linear regression helps identify correlations between variables, such as the relationship between project delays and contractor resource allocation. Logistic regression, on the other hand, is effective for binary outcomes, such as predicting whether a contractor will default on a project based on historical performance. Time series analysis provides insights into temporal trends, enabling stakeholders to anticipate risks tied to seasonal fluctuations or long-term performance trajectories. These models rely on clearly defined assumptions about data distribution and relationships, making them particularly useful for analyzing structured data sets where the underlying patterns are relatively stable and well understood. The advent of machine learning has expanded the capabilities of risk forecasting by introducing algorithms that can process vast amounts of data, detect nonlinear relationships, and adapt to changing conditions. Unlike traditional statistical models, which often require predefined assumptions, machine learning algorithms excel in uncovering hidden patterns and generating predictions from complex, unstructured datasets. Decision trees, random forests, support vector machines, and neural networks are among the machine learning techniques commonly applied to contractor risk assessment. For example, random forests can aggregate multiple decision trees to create robust ensemble-based predictions, while neural networks can model intricate, multidimensional relationships in data, such as the interaction between contractor experience, project scope complexity, and external market conditions. These algorithms are particularly effective in high-dimensional spaces, where the number of variables and interactions may exceed human comprehension, offering a level of analytical depth that was previously unattainable. Dynamic risk forecasting models represent the next evolution in predictive analytics, allowing for continuous updates and refinements as new data is incorporated. These models are built on the principles of Bayesian inference and reinforcement learning, which emphasize adaptability and iterative learning. Bayesian models update risk probabilities based on the arrival of new evidence, ensuring that predictions remain accurate as conditions change. For instance, if a contractor consistently demonstrates improved performance on recently completed projects, a Bayesian model will adjust its risk assessment to reflect this trend, reducing the contractor's perceived risk over time. Reinforcement learning, a subset of machine learning, further enhances dynamic modeling by enabling algorithms to learn optimal strategies through trial and error. In the context of contractor risk assessment, reinforcement learning models can simulate various scenarios, such as changes in project funding, scope adjustments, or regulatory shifts, and identify strategies that minimize risk while maximizing project success. The practical applications of risk forecasting models are diverse and far-reaching, spanning project planning, underwriting decisions, and risk mitigation strategies. In project planning, these models help stakeholders allocate resources efficiently, set realistic timelines, and anticipate potential challenges. For example, a forecasting model may identify a high likelihood of supply chain disruptions based on historical data, prompting contractors to secure alternative suppliers or build contingency plans. In underwriting, risk forecasting models provide a data-driven foundation for determining bond limits, premiums, and collateral requirements. By integrating historical performance data with predictive analytics, underwriters can assess the likelihood of contractor default with greater accuracy, reducing financial exposure and improving portfolio performance. Risk mitigation strategies also benefit from forecasting models, which can identify early warning signs of project failure and enable proactive interventions, such as renegotiating contracts, reallocating resources, or adjusting project timelines. Interdisciplinary connections enhance the design and application of risk forecasting models, drawing on fields such as mathematics, computer science, behavioral economics, and operations research. Mathematics provides the theoretical underpinnings for statistical and machine learning algorithms, including probability theory, optimization, and linear algebra. Computer science contributes the computational tools and frameworks needed to implement these algorithms, such as programming languages, data processing pipelines, and cloud computing platforms. Behavioral economics offers insights into the human factors that influence contractor performance, such as decision-making biases, risk aversion, and incentive structures, which can be incorporated into predictive models to account for non-quantifiable variables. Operations research applies optimization techniques to improve resource allocation, scheduling, and risk management, ensuring that forecasting models align with practical decision-making processes. Contemporary debates in risk forecasting often focus on the trade-offs between model complexity and interpretability, as well as the ethical implications of predictive analytics. While complex machine learning models, such as deep neural networks, offer unparalleled predictive accuracy, their black box nature can make it difficult to explain how predictions are generated, raising concerns about transparency and accountability. This lack of interpretability is particularly problematic in high-stakes decisions, where stakeholders must justify their actions to regulators, clients, or investors. Addressing this challenge requires the development of explainable artificial intelligence, XAI techniques, which aim to make complex models more transparent and interpretable without sacrificing performance. Ethical considerations also play a significant role, particularly in the use of personal or sensitive data for risk forecasting. Ensuring data privacy, preventing bias, and promoting fairness are critical challenges that must be addressed to maintain stakeholder trust and comply with regulatory standards. The historical evolution of risk forecasting models reflects broader advancements in data science and computational technology. Early models were primarily statistical, relying on manual calculations and limited data sets to generate predictions. The development of electronic databases and statistical software in the mid-20th century marked a turning point, enabling more sophisticated analyses and larger-scale applications. The emergence of machine learning in the late 20th and early 21st centuries further revolutionized the field, introducing algorithms capable of processing unstructured data, such as text, images, and sensor readings. Today, the integration of big data, cloud computing, and artificial intelligence has transformed risk forecasting into a dynamic and scalable process, capable of delivering real-time insights across diverse domains. Emerging trends in risk forecasting emphasize the integration of external data sources, such as satellite imagery, social media activity, and macroeconomic indicators, to enhance predictive accuracy. For instance, satellite imagery can provide real-time updates on construction progress, environmental conditions, or geographic risks, while social media sentiment analysis can gauge public perceptions of a contractor or project. Macroeconomic indicators, such as inflation rates, interest rates, and unemployment levels, offer additional context for understanding the broader economic forces that influence contractor risk. The incorporation of these data sources requires advanced data fusion techniques, which combine heterogeneous data sets into a unified analytical framework, enabling more comprehensive and context-aware risk assessments. Legal and regulatory compliance in past projects is a critical dimension of contractor evaluation, serving as a barometer of a contractor's ability to navigate the complex web of safety standards, environmental laws, and industry-specific regulations. Adherence to these requirements is not merely a matter of operational discipline, but a reflection of organizational culture, risk management capability, and ethical responsibility. For underwriters, assessing compliance history offers a nuanced perspective on contractor reliability, revealing patterns of behavior that may indicate future liabilities or risks. Regulatory compliance is a multifaceted construct, encompassing federal, state, and local mandates, as well as international standards for contractors operating in global markets. Each layer of regulation introduces unique challenges, and contractors must demonstrate both the technical competence and procedural rigor to meet these standards consistently. The assessment of regulatory compliance begins with a thorough review of past projects, focusing on documented adherence to safety protocols, environmental regulations, and contractual obligations. Safety standards are a cornerstone of this evaluation, as they directly impact the well-being of workers, the public, and the built environment. For example, compliance with the Occupational Safety and Health Administration, OSHA regulations in the United States, is a baseline expectation for contractors, ensuring that job sites are free from hazards and that workers receive proper training and protective equipment. Non-compliance in this area is often accompanied by fines, work stoppages, and reputational damage, all of which have cascading effects on project timelines and budgets. Historical data on safety violations, accident rates, and inspection outcomes provide quantitative metrics for evaluating a contractor's safety performance, while qualitative insights can be gleaned from worker testimonies, audit reports, and third-party evaluations. Environmental laws represent another critical dimension of compliance, reflecting the growing emphasis on sustainability and ecological responsibility in the construction and infrastructure sectors. Contractors must navigate a labyrinth of environmental regulations, such as the Clean Water Act and Clean Air Act in the United States, which impose strict standards for pollution control, waste management, and resource conservation. Compliance with these laws requires meticulous planning, ongoing monitoring, and proactive mitigation strategies to minimize environmental impact. Historical instances of non-compliance, such as unauthorized discharges, deforestation, or violations of emission standards, serve as red flags in risk assessment, indicating potential vulnerabilities in the contractor's environmental management practices. Furthermore, the legal and financial repercussions of environmental violations, including lawsuits, remediation costs, and loss of community trust, underscore the high stakes associated with this aspect of regulatory compliance. The implications of compliance issues extend beyond the immediate consequences of fines and penalties, influencing underwriting decisions and broader risk management strategies. For underwriters, a contractor's compliance history provides a valuable predictor of future behavior, shaping the terms and conditions of bonding agreements. Contractors with a strong track record of regulatory adherence are viewed as lower-risk candidates, often receiving favorable bond terms, higher bonding limits, and lower premiums. Conversely, contractors with a history of violations or unresolved compliance issues face stricter underwriting requirements, such as increased collateral demands, more frequent audits, or even exclusion from certain projects. The integration of compliance data into underwriting models requires a careful balancing of quantitative and qualitative factors, ensuring that risk assessments are both comprehensive and contextually grounded. The theoretical frameworks underpinning compliance evaluation draw on principles from law, organizational behavior, and risk management. Legal theories, such as deterrence theory, suggest that the severity and certainty of penalties influence compliance behavior, highlighting the importance of robust enforcement mechanisms in shaping contractor practices. Organizational behavior frameworks, such as institutional theory, explore how contractors internalize regulatory norms and integrate them into their operational processes. For instance, contractors that institutionalize compliance through formal training programs, dedicated compliance officers, and real-time monitoring systems are better equipped to meet regulatory requirements and respond to emerging challenges. Risk management theories, such as the precautionary principle, emphasize the proactive identification and mitigation of compliance risks, encouraging contractors to exceed minimum standards and adopt best practices. Interdisciplinary connections further enrich the analysis of regulatory compliance, integrating insights from environmental science, economics, and sociology. Environmental science provides the technical expertise needed to assess the ecological impact of construction activities, from soil erosion and water contamination to carbon emissions and habitat disruption. Economics offers tools for quantifying the cost-benefit trade-offs of compliance investments, such as the long-term savings associated with energy-efficient designs or pollution prevention measures. Sociology examines the social dimensions of compliance, including the role of public perception, community engagement, and stakeholder trust in shaping contractor behavior. For example, a contractor that engages with local communities to address environmental concerns may not only improve compliance outcomes, but also enhance project support and reduce the risk of opposition or litigation. Contemporary debates in regulatory compliance often revolve around the tension between prescriptive regulations and performance-based standards. Prescriptive regulations specify detailed requirements for compliance, providing clear benchmarks but often limiting flexibility and innovation. Performance-based standards, by contrast, focus on outcomes rather than processes, allowing contractors to adopt customized approaches that align with their unique capabilities and project contexts. While performance-based standards offer greater adaptability, they also require more rigorous monitoring and enforcement to ensure that desired outcomes are achieved. This debate is particularly relevant in emerging areas such as green building certifications, where the balance between regulatory oversight and market-driven innovation remains a topic of ongoing discussion. The role of technology in enhancing regulatory compliance has become increasingly prominent, with digital tools and data analytics transforming traditional approaches to monitoring and enforcement. Geographic Information Systems, GIS, and remote sensing technologies enable real-time tracking of environmental impacts such as deforestation, water quality changes, and land use patterns. Similarly, wearable devices and Internet of Things, IoT sensors enhance worker safety by monitoring exposure to hazardous conditions, tracking fatigue levels, and ensuring adherence to safety protocols. Advanced data analytics platforms integrate these technologies with historical compliance data, enabling predictive modeling and early warning systems that alert contractors to potential violations before they occur. Blockchain technology offers additional benefits by creating immutable records of compliance activities, reducing the risk of fraud, and ensuring transparency in reporting and auditing processes. The historical evolution of regulatory compliance reflects broader trends in governance, industrialization, and social accountability. Early regulatory frameworks were often reactive, emerging in response to high-profile incidents such as workplace accidents, environmental disasters, or public health crises. Over time, these frameworks have become more proactive and comprehensive, reflecting advancements in scientific knowledge, legal systems, and public expectations. For example, the establishment of OSHA in 1971 marked a significant milestone in workplace safety regulation, setting enforceable standards and creating mechanisms for inspection and enforcement. Similarly, the rise of environmental regulations in the latter half of the 20th century, driven by growing awareness of ecological degradation, has reshaped the responsibilities of contractors and the expectations of stakeholders. Emerging trends in regulatory compliance emphasize the integration of global standards, cross-industry collaboration, and sustainability metrics. Global standards, such as those established by the International Organization for Standardization, ISO, provide a consistent framework for evaluating compliance across different jurisdictions and industries, facilitating international projects and reducing regulatory fragmentation. Cross-industry collaboration fosters the sharing of best practices, technologies, and innovations, enabling contractors to address complex compliance challenges more effectively. Sustainability metrics, such as those outlined in the United Nations Sustainable Development Goals, SDGs, encourage contractors to align their practices with broader societal objectives, integrating environmental stewardship, social responsibility, and economic resilience into their compliance strategies. These trends highlight the evolving nature of regulatory compliance, underscoring its centrality in shaping the future of contractor performance and project outcomes. Benchmarking contractor performance across similar projects is a fundamental practice in risk assessment, providing a structured framework for evaluating contractors against industry standards and identifying deviations that may signal potential risks or competitive advantages. The process involves comparing key performance indicators, such as cost efficiency, schedule adherence, and quality outcomes, with benchmarks derived from similar project types, sizes, and geographic regions. These comparisons enable stakeholders to contextualize contractor performance within broader market conditions, ensuring that evaluations account for industry variability and regional nuances. By integrating benchmarking into risk assessment, underwriters, project owners, and investors gain a nuanced understanding of contractor capabilities, allowing for more accurate forecasting of future performance and tailored risk mitigation strategies. The foundation of benchmarking lies in the systematic collection and analysis of industry data, encompassing historical project outcomes, contractor records, and market trends. Industry benchmarks are typically established through the aggregation of performance data from multiple projects, creating a baseline against which individual contractors can be assessed. For example, benchmarks for construction projects might include average cost per square foot, typical project duration for specific building types, and standard defect rates. These benchmarks vary by region, reflecting differences in labor costs, material availability, and regulatory environments. To ensure meaningful comparisons, it is essential to select benchmarks that align closely with the characteristics of the project under evaluation, such as its scale, complexity, and sector-specific requirements. Comparing contractor performance to industry benchmarks involves both quantitative and qualitative analyses. Quantitative metrics, such as cost variance and schedule performance index, provide objective measures of contractor efficiency and reliability. For instance, if a contractor consistently completes projects below the benchmarked cost per square foot, this may indicate superior resource management or negotiation skills. Conversely, frequent cost overruns relative to industry standards could signal inefficiencies, poor planning, or external challenges. Qualitative factors such as client feedback, subcontractor relationships, and adaptability to unforeseen challenges add depth to the analysis by capturing dimensions of performance that are not easily quantified. Integrating these perspectives creates a comprehensive profile of contractor capabilities, highlighting areas of strength and potential concern. Geographic variability is a critical consideration in benchmarking, as regional factors can significantly influence project performance. Labor market dynamics, for example, vary widely between urban and rural areas, affecting both the availability and cost of skilled workers. Similarly, material costs may fluctuate based on proximity to suppliers, transportation infrastructure, and local demand. Regulatory requirements, such as building codes and environmental standards, also differ by region, introducing additional complexity to project execution. Benchmarking must account for these regional disparities to ensure that contractor performance is evaluated within the appropriate context. For instance, a contractor operating in a high-cost metropolitan area should not be penalized for higher project expenses if their cost efficiency aligns with regional benchmarks. This contextualization is essential for fair and accurate assessments, enabling stakeholders to distinguish between performance issues that are contractor-specific and those driven by external conditions. Adjusting risk assessments to account for market conditions and industry variability is a dynamic process that requires ongoing monitoring and analysis. Market conditions, such as fluctuations in material prices, interest rates, and economic growth, can significantly impact project outcomes and contractor performance. For example, a sudden increase in steel prices may lead to cost overruns in infrastructure projects, while a downturn in the housing market could reduce demand for residential construction. Industry variability, such as shifts in technology adoption or changes in consumer preferences, also shapes the competitive landscape, influencing contractor capabilities and risks. To address these factors, risk assessments must incorporate real-time data and predictive analytics, enabling stakeholders to adapt to changing conditions and anticipate potential challenges. Theoretical frameworks for benchmarking draw on principles from economics, operations management, and competitive strategy. Economic theories, such as cost-benefit analysis and market equilibrium, provide tools for evaluating the efficiency and feasibility of contractor practices relative to industry norms. Operations management frameworks, such as Lean Construction and Six Sigma, emphasize process optimization and continuous improvement, offering benchmarks for productivity, waste reduction, and quality control. Competitive strategy models, such as Porter's 5 Forces, analyze the broader market environment, identifying factors that influence contractor performance, such as supplier bargaining power and industry rivalry. These frameworks inform the selection and interpretation of benchmarks, ensuring that evaluations are grounded in rigorous and contextually relevant analyses. Interdisciplinary connections enhance the benchmarking process by integrating insights from data science, sociology, and environmental studies. Data science provides the computational tools and algorithms needed to process large data sets, identify patterns, and generate predictive models. For example, machine learning techniques can cluster similar projects based on performance characteristics, enabling more precise benchmarking comparisons. Sociology examines the social dynamics that influence contractor performance, such as organizational culture, workforce diversity, and stakeholder relationships. Environmental studies contribute to the understanding of sustainability metrics, such as carbon footprint and energy efficiency, which are increasingly incorporated into industry benchmarks. These interdisciplinary perspectives enrich the benchmarking process, creating a holistic framework for evaluating contractor performance and risks. Contemporary debates in benchmarking often focus on the balance between standardization and customization. Standardized benchmarks offer the advantage of comparability, enabling stakeholders to assess contractor performance across different projects and regions using consistent metrics. However, critics argue that rigid benchmarks may oversimplify complex realities, failing to capture unique project characteristics or contractor-specific challenges. Customization, by contrast, allows for tailored benchmarks that reflect the distinct needs and priorities of individual stakeholders or projects. For example, a benchmark for green building projects might prioritize sustainability metrics, such as energy efficiency and renewable material usage, over traditional cost and schedule indicators. Balancing these approaches requires the development of flexible benchmarking frameworks that accommodate both standardization and customization without compromising analytical rigor. The historical evolution of benchmarking reflects broader trends in project management and data-driven decision-making. Early benchmarking practices were often informal and qualitative, relying on anecdotal evidence and subjective judgment to compare contractor performance. The advent of statistical analysis and standardized reporting in the mid-20th century introduced more structured and objective approaches, enabling the creation of industry benchmarks based on empirical data. In recent decades, advances in digital technology and big data analytics have further transformed benchmarking, allowing for the integration of real-time data, predictive modeling, and automated reporting. These advancements have expanded the scope and accuracy of benchmarking, enabling stakeholders to evaluate contractor performance with unprecedented depth and precision. Emerging trends in benchmarking emphasize the integration of sustainability metrics, technology adoption, and global standards. Sustainability metrics, such as those outlined in the Leadership in Energy and Environmental Design (LEED) certification system, provide benchmarks for evaluating the environmental and social impact of construction projects. Technology adoption, including the use of building information modeling (BIM) and advanced construction materials, introduces new benchmarks for efficiency, accuracy, and innovation. Global standards, such as those established by the International Organization for Standardization (ISO), offer a consistent framework for benchmarking across international projects, facilitating cross-border collaboration and competition. These trends highlight the evolving nature of benchmarking, reflecting the changing priorities and expectations of stakeholders in the construction and infrastructure sectors. Risk indicators in contractor subcontracting practices are critical to understanding the dynamics of project execution and the potential vulnerabilities that arise from the delegation of work. Subcontracting is an integral part of construction and infrastructure projects, enabling contractors to access specialized expertise, scale their operations, and manage complex projects efficiently. However, the reliance on subcontractors introduces layers of risk that must be carefully evaluated, including the criteria for selecting subcontractors, the systems in place for overseeing their performance, and the practices governing their payment. These factors not only impact project outcomes, but also influence the financial stability and reputation of the primary contractor. Identifying patterns in subcontracting practices that may pose additional risk is essential for creating robust risk assessment models and ensuring successful project delivery. The evaluation of subcontractor selection criteria is a foundational step in assessing subcontracting risk. Contractors typically choose subcontractors based on a combination of technical expertise, past performance, financial stability, and cost competitiveness. However, the weight given to these factors can vary significantly across contractors and projects, leading to disparities in the quality and reliability of subcontractors. For instance, prioritizing low-cost bids without adequate consideration of quality or capacity can result in subcontractors who are ill-equipped to meet project demands, increasing the likelihood of delays, rework, or disputes. Theoretical frameworks, such as transaction cost economics, provide a lens through which to analyze these decisions, emphasizing the trade-offs between cost savings and the risks of opportunism or underperformance. In practice, rigorous pre-qualification processes, including background checks, reference verifications, and financial audits, are essential for mitigating these risks and ensuring that subcontractors meet the required standards of competence and reliability. Performance oversight is another critical dimension of subcontracting risk, reflecting the contractor's ability to monitor and manage subcontractor activities throughout the project lifecycle. Effective oversight involves establishing clear performance metrics, conducting regular inspections, and maintaining open communication channels with subcontractors. Metrics such as adherence to schedules, quality of workmanship, and compliance with safety standards provide objective benchmarks for evaluating subcontractor performance. However, the complexity of managing multiple subcontractors across diverse trades can create coordination challenges, particularly in large-scale projects with overlapping timelines and interdependent tasks. Systems theory offers valuable insights into these dynamics, highlighting the importance of integration and feedback mechanisms in maintaining overall project stability. For example, project management software that tracks subcontractor progress in real time can facilitate early identification of performance issues, enabling proactive interventions that minimize disruptions and ensure alignment with project goals. Payment practices further influence subcontracting risk, as they directly affect subcontractor motivation, financial health, and capacity to deliver on contractual obligations. Timely payments are essential for ensuring that subcontractors can maintain cash flow, procure materials, and pay their own workers and suppliers. Delays or inconsistencies in payment can create cascading effects, leading to work stoppages, disputes, or even subcontractor insolvency. Historical data on payment practices provides valuable indicators of risk, revealing patterns of delayed payments, disputes over change orders, or high rates of lien filings. Additionally, payment structures such as milestone-based payments, retainage, or performance incentives can influence subcontractor behavior, incentivizing efficiency and quality, but also introducing potential conflicts if not managed transparently. Legal frameworks, such as the Prompt Payment Act in the United States, establish minimum standards for payment timelines, underscoring the importance of regulatory compliance in mitigating subcontracting risks. Identifying subcontracting patterns that pose additional risk requires a holistic analysis of historical project data, contractor practices, and market conditions. One common risk indicator is excessive reliance on a small pool of subcontractors, which can create vulnerabilities if those subcontractors face capacity constraints, financial difficulties, or performance issues. Conversely, frequent turnover among subcontractors may indicate instability in subcontracting relationships, raising concerns about the contractor's ability to maintain long-term partnerships or ensure consistency and quality. Geographic patterns also play a role, as subcontractors operating in remote or high-risk regions may face unique challenges, such as logistical constraints, labor shortages, or regulatory hurdles. Advanced data analytics techniques, including clustering algorithms and network analysis, can uncover these patterns and provide actionable insights for risk assessment. The implications of subcontracting risks extend beyond individual projects, influencing broader contractor performance, reputation, and financial stability. For underwriters, these risks are critical factors in evaluating bond eligibility, setting limits, and determining premiums. Contractors with well-documented subcontracting practices, strong oversight mechanisms, and a history of timely payments are generally viewed as lower-risk candidates, while those with frequent subcontractor disputes or payment issues face stricter underwriting requirements. The integration of subcontracting data into underwriting models allows for a more granular assessment of risk, capturing dimensions of performance that may not be evident from aggregate project metrics. For example, a contractor with a strong overall track record but recurring issues with subcontractor safety violations may face increased scrutiny, as these violations can signal systemic weaknesses in oversight or compliance. Interdisciplinary approaches to analyzing subcontracting risks draw on fields such as supply chain management, organizational behavior, and behavioral economics. Supply chain management provides frameworks for understanding the flow of resources, information, and payments between contractors and subcontractors, highlighting the importance of coordination and transparency in reducing disruptions. Organizational behavior examines the relational dynamics between contractors and subcontractors, exploring factors such as trust, communication, and conflict resolution that influence performance outcomes. Behavioral economics offers insights into decision-making processes, such as how contractors weigh the risks and rewards of subcontracting decisions, or how subcontractors respond to payment incentives or penalties. These interdisciplinary perspectives enrich the analysis of subcontracting risks, creating a more comprehensive framework for understanding and mitigating vulnerabilities. Contemporary debates in subcontracting practices often focus on the balance between flexibility and control. Flexibility in subcontracting allows contractors to adapt to changing project requirements, access specialized expertise, and scale operations efficiently. However, excessive flexibility can lead to a lack of accountability, fragmented oversight, and inconsistent quality. Conversely, strict control mechanisms such as detailed contracts, rigid performance metrics, or frequent audits can ensure accountability but may stifle innovation, increase administrative burdens, or strain subcontractor relationships. Finding the optimal balance requires a nuanced approach that considers project-specific factors, such as complexity, timeline, and risk tolerance, as well as broader industry trends and stakeholder priorities. The historical evolution of subcontracting practices reflects broader changes in the construction and infrastructure sectors, including shifts toward specialization, globalization, and digitalization. In the mid-20th century, general contractors often performed a majority of project tasks in-house, relying on subcontractors primarily for specialized trades such as electrical or plumbing work. Over time, the increasing complexity and scale of projects, coupled with advances in construction technology and management practices, have led to greater reliance on subcontractors across all phases of project execution. Today, subcontractors often account for a significant portion of project work, highlighting the need for robust systems to manage subcontracting risks and ensure alignment with project objectives. Emerging trends in subcontracting practices emphasize the integration of digital technologies, sustainability goals, and workforce development initiatives. Digital tools such as building information modeling, BIM, IoT-enabled sensors, and blockchain platforms enhance transparency and coordination in subcontracting relationships, reducing risks associated with miscommunication or data discrepancies. Sustainability goals, such as those outlined in green building certifications, influence subcontractor selection criteria, prioritizing firms with expertise in energy-efficient designs, renewable materials, or low-impact construction methods. Workforce development initiatives, such as training programs and apprenticeship opportunities, address labor shortages and skill gaps, ensuring that subcontractors can meet the evolving demands of modern construction projects. These trends highlight the dynamic and multifaceted nature of subcontracting risks, underscoring the importance of continuous adaptation and innovation in managing contractor-subcontractor relationships. Integrating qualitative and quantitative risk indicators into a cohesive framework represents a critical advancement in contractor risk assessment, allowing for a balanced and comprehensive evaluation of contractor reliability. Quantitative indicators such as financial metrics, performance indices, and compliance records provide measurable and objective benchmarks that form the foundation of traditional risk analysis. These indicators are essential for evaluating key aspects of contractor performance, such as financial stability, operational efficiency, and adherence to contractual obligations. However, the limitations of purely quantitative approaches become evident when contextual or subjective factors significantly influence contractor outcomes. Qualitative insights, including reputation, client feedback, and organizational culture, capture the subtler dimensions of risk that are not easily quantified but are equally critical to understanding contractor reliability. Combining these two dimensions through the development of composite risk scores enables a more nuanced and holistic assessment, bridging the gap between measurable performance and contextual understanding. Quantitative risk indicators are derived from structured data sources, including financial statements, project schedules, and compliance reports. These indicators are valuable for identifying patterns and trends that signal potential risks. For instance, financial metrics such as liquidity ratios, debt-to-equity ratios, and cash flow stability provide insights into a contractor's ability to manage resources and meet financial obligations. Similarly, performance indices, such as Cost Performance Index and Schedule Performance Index, measure operational efficiency and adherence to project timelines. These metrics are often aggregated across multiple projects to establish benchmarks, enabling comparisons between contractors and within industry standards. However, while quantitative data offers precision and consistency, it is inherently limited by the scope and granularity of available datasets. For example, financial metrics may reveal liquidity issues but fail to explain their underlying causes, such as poor client relationships or disputes over change orders. These limitations underscore the importance of integrating qualitative insights to capture the broader context of contractor performance. Qualitative risk indicators provide the contextual depth needed to complement and enhance quantitative analyses. Reputation is a key qualitative factor, reflecting the contractor's standing within the industry, as perceived by clients, subcontractors, and other stakeholders. Reputation is shaped by factors such as project delivery history, dispute resolution practices, and responsiveness to stakeholder concerns. Client feedback further enriches this dimension, offering first-hand accounts of contractor behavior, including adaptability, communication, and conflict management. Organizational culture is another critical qualitative indicator, influencing how contractors approach risk, innovation, and collaboration. For example, a contractor with a culture of transparency and accountability may be better equipped to manage complex projects and maintain stakeholder trust than one with a history of opacity or blame shifting. These qualitative factors are typically gathered through interviews, surveys, and case studies, requiring careful interpretation to ensure reliability and relevance. Developing composite risk scores involves integrating quantitative and qualitative indicators into a unified framework that captures the multidimensional nature of contractor risk. This process begins with the selection and weighting of relevant indicators, reflecting their relative importance to the overall risk profile. For instance, financial metrics may carry greater weight in assessing liquidity risks, while qualitative insights may be more critical for evaluating reputational risks. Statistical methods, such as principal component analysis or factor analysis, are often used to identify the underlying dimensions of risk and reduce redundancy among indicators. Machine learning algorithms, including regression models and decision trees, can further refine composite scores by identifying nonlinear relationships and interactions between indicators. The resulting scores provide a single, interpretable metric that encapsulates the complexity of contractor risk, enabling stakeholders to make more informed and consistent decisions. The theoretical underpinnings of integrating qualitative and quantitative indicators draw on disciplines such as decision science, risk management, and behavioral economics. Decision science emphasizes the importance of combining diverse data sources to improve the accuracy and robustness of risk assessments. Risk management frameworks, such as the ISO 31000 standard, advocate for a holistic approach that considers both measurable and contextual factors in identifying, analyzing, and mitigating risks. Behavioral economics highlights the cognitive biases that can influence the interpretation of qualitative insights, such as anchoring on recent events or overemphasizing negative feedback. These theoretical perspectives inform the design of composite risk scores, ensuring that they reflect both the objective and subjective dimensions of contractor performance. Practical applications of composite risk scores extend across project planning, underwriting, and performance monitoring. In project planning, composite scores enable stakeholders to evaluate contractor suitability for specific projects, balancing financial stability with contextual factors such as regional expertise or client relationships. In underwriting, composite scores provide a data-driven basis for determining bond eligibility, limits, and premiums, reducing the reliance on subjective judgment and enhancing consistency across evaluations. Performance monitoring benefits from composite scores by identifying early warning signs of emerging risks, enabling proactive interventions to address issues before they escalate. For example, a sudden decline in a contractor's composite score, driven by deteriorating client feedback or financial metrics, may prompt closer scrutiny and additional support to ensure project success. Interdisciplinary connections enrich the integration of qualitative and quantitative indicators, drawing on insights from sociology, data science, and organizational psychology. Sociology examines the social networks and relationships that shape contractor reputation and influence stakeholder perceptions. Data science provides the computational tools needed to process large and diverse data sets, identify patterns, and generate predictive models. Organizational psychology explores the cultural and behavioral factors that drive contractor decision-making, offering insights into how qualitative indicators such as leadership style or team dynamics impact performance. These interdisciplinary perspectives create a more comprehensive framework for integrating risk indicators, ensuring that composite scores capture the full spectrum of contractor reliability. Contemporary debates in the integration of qualitative and quantitative risk indicators focus on issues of data reliability, transparency, and ethical considerations. Data reliability is a key challenge, particularly for qualitative indicators, which are often subject to bias, inconsistency, and limited availability. Transparency is another critical issue, as composite risk scores must be interpretable and explainable to ensure stakeholder trust and accountability. Ethical considerations, such as privacy and fairness, arise when using sensitive or subjective data in risk assessments, requiring the development of robust governance frameworks to address these concerns. For example, ensuring that client feedback is anonymized and representative reduces the risk of bias while maintaining the integrity of qualitative insights. The historical evolution of risk assessment reflects the increasing emphasis on integrating diverse data sources to improve decision-making. Early approaches to risk assessment were primarily qualitative, relying on expert judgment and anecdotal evidence to evaluate contractor performance. The advent of financial analysis and statistical modeling in the mid-20th century introduced a more quantitative focus, enabling standardized evaluations based on measurable metrics. In recent decades, advances in technology and data science have facilitated the integration of qualitative and quantitative indicators, creating more sophisticated and comprehensive risk assessment frameworks. This evolution highlights the dynamic and iterative nature of risk assessment, driven by the ongoing pursuit of accuracy, consistency, and context in evaluating contractor reliability. Emerging trends in the integration of risk indicators emphasize the use of artificial intelligence, natural language processing, and real-time data analytics. Artificial intelligence enables the development of more advanced models for combining qualitative and quantitative data, incorporating features such as adaptive learning and scenario analysis. Natural language processing enhances the analysis of qualitative insights, extracting actionable information from unstructured data sources such as client reviews, social media posts, and project documentation. Real-time data analytics supports the continuous updating of composite risk scores, ensuring that assessments remain accurate and relevant as new information becomes available. These trends highlight the transformative potential of technology in advancing the integration of risk indicators, creating more dynamic and robust frameworks for contractor risk assessment.